Greetings everyone. My name is Sharan Tumugunti and we'll be presenting on the topic real-time data analysis of data servers using Apache Hadoop, Spark, and Kafka on Docker. Demand for new efficient methods for processing large-scale heterogeneous data in real time is growing. In many data centers, different types of servers generate large amounts of data events, in this case being the status of the server in the data center in real time. Currently, there is a need to process this data in real time and generate insights which will be used by the data server manager who have to track the server's status regularly and find the resolution in case of issues occurring for better server stability. Since the data is huge and generated in real time, we need to choose the right architecture with scalable storage and computational frameworks or technologies. We're going to demonstrate an efficient and low latency streaming pipeline to ensure real-time data analysis using various big data frameworks like Apache Kafka, Spark, Hadoop, Postgres, Django, and FlexMonster on Docker to generate insights out of the server-generated data.
Myself RNTN, I will be explaining the use case diagram of a model. As we don't have access to a live feed of server data, we create a Python simulator that generates event containing the status of the server in the data center for every 1 second. Some of the fields that event are the event ID, server status, security level, the server location, the time and date of the event generation, and estimated time to resolve the issue, which is prediction made based off the historical data. The event has to be published to the Kafka producer, which acts as an intermediate buffer holding the streaming data before it is sent to processing. These events are then consumed from the Kafka topic using Spark structured streaming where the data manipulation, transformation, and aggregation is performed. The raw data is stored in a persistent, persistent storage like HDFS, and the aggregated results are stored in PostgreSQL database team. The aggregated data is then visualized from the charts, graphs, and tabular visualization using Django and FlexMonster.
So let us understand what data ingestion means. Data ingestion is the process of importing large assorted data files from multiple resources into a single cloud-based storage medium. Now, in this project, we had a lot of raw data that contained many fields like server severity status, event date and time, event server type, country code, etc. And what we aim for is to get the severity level and the estimated resolution time of the issue, which means how urgent it is to give attention to a server or how urgent it is to take action. Now, as you can see on the screen, there are three color codes that are shown that show the server status. That tells us about the levels of severity or urgency. Now, green or severity level 3 represents small bugs and warnings that don't necessarily affect the server's performance. Secondly, orange or server level 2 represents a minor issue that is affecting the server's performance and availability. Red or server level severity level 1 represents a major issue, mostly resulting in server being down or requiring immediate action. Now, one of our aims is this, that is to identify the severity of the servers. Now, data ingestion is performed using Kafka. Now, the reason that we have used Kafka for this is that it is fault tolerant. That is, if we want to have a storage medium for the events, which is also in a distributed manner, so Kafka is the right option because it also has high resilience and eases the process of data ingestion. Kafka employs two functions. One is producer and the other is consumer to read, write, and process events. Producer acts as an interface between the simulator and the topics, and consumers allow us to read and transfer the data stored in Kafka. The Kafka message broker handles the serving and delivery of data throughout the streaming data pipeline. Now we'll understand this better with the code demonstration. In this code, there is topic name cons that has been defined. It is the name of the Kafka topic to which messages will be produced. Raw data is obtained and converted into JSON objects, which is captured by a Bootstrap server to store them in the server live status topic. Secondly, we have the Bootstrap server cons, which is the address of the Kafka broker. Then we have the random user API URL, which stores the URL endpoint for the random user API. To elaborate more, API helps it communicate with each other using requests and response by making a GET request to this URL. You can retrieve JSON formatted data containing random user information. Further, we initialize an object named Kafka producer object, and then after that, we specify the severity in the Kafka producer object. Then we create a list of all the servers from which the event has been generated. As you can see in the code, we make a GET request to this URL that helps us retrieve random user information. Now we are processing the raw data by adding it to a dictionary and specifying the correct data format for each field where necessary. Then we are sending the data to the topic for processing. Here we are starting the data center code and we can see the events being generated. Now let us start a demo to see that the events from Kafka Producer are being consumed by the consumer.
My name is Ayushi Padia and I'll be explaining to you stream processing and schema standardization. The the streaming pipeline acts as a consumer job that consumes the raw data stored in the Kafka topic of server live status, which is obtained from the Bootstrap server on which the Kafka producer is running. In order to prepare and analyze the streaming data, it must be consistently structured into a standard schema, a guide that determines and understands how data is organized. Adhering to a standard schema enables scalable data compatibility while reducing operational complexity. This can be achieved using the struct type class in Python and listing the schema fields using struct field class. We specify the read stream method in which format we are expecting our data, the Kafka Bootstrap server IP address from which the data needs to be consumed, and the topic name having the data. Next, we are extracting the raw data into the schema from the Kafka topic through the value field, which is stored in the HDFS. The data then undergoes transformation through aggregation and summation through mini batches, as in case there exists more data than the pipeline can consume at that given moment. It only consumes the amount of data it can handle as a batch and processes the stream of events in the form of mini batches until all events have been consumed. This process is set to run every 20 seconds until the streaming program is terminated. A write stream method is used to store this raw data into the HDFS. Another write stream method to create the event checkpoints from which the streaming process can continue in case the pipeline is terminated and restarted. And a third write stream method is used to store the transformed results into the Postgres database by establishing a connection via a JDBC connector. Now we are going to start the command for starting Spark streaming pipeline.
Now we will be explaining the data visualization part of our model. For the website, to be able to retrieve the data from the database, we need to create a table model class that specifies the schema structure of the result. The model and table, which needs to be accessed, is then migrated to make necessary changes in the database and create the connection between the website and database. We can then view the raw tabular data, different varieties of graphs and charts such as pie chart, bar graph, line chart, stacked bar graph, and so on using FlexMonster. This is done by reading the aggregated result in the form of list of JSON objects. To create our the dataset, and dataset is plotted in the chart format we want based on the configurations settings we specify in the FlexMonster object.
Now that we have our processed data from our mini batches stored into our database, let's have a look at our website. Here we can see a pie chart of the total message count from each country and a bar graph version of the data server messages. We also have a view of the aggregated data stored in the database. We can also change the field on which we want to create a visualization and change the type of chart as well to something like bar graph, line graph, or a scatter plot.
These are the project's future potential. Firstly, data security and compliance. Real-time data analysis can help organizations detect and respond to security threats or compliance issues more effectively. Secondly, we have predictive analytics. By leveraging historical server data and advanced predictive analytics, the project can forecast future traffic patterns and anticipate potential server overload scenarios before they occur. Thirdly, we have business impact. So, by minimizing downtime, improving service reliability, and enhancing user experience, any business could attract more customers.
We deem it a pleasure to acknowledge our sense of gratitude to our project guide, Dr. Animesh Chaturvedi, under whom we have carried out the project work. We shall remain grateful to him for providing us a strong academic atmosphere and valuable suggestions that encouraged us to do the project work and learn new technologies. And this is the GitHub link for our project.